Hi everyone, in today's video, let's talk about the method of mathematical induction. If you are already an expert in this method, you probably already know the intuition and logic behind the method, but there's always no harm for a little refresher. However, if you have just learned induction in school, you might have learned the method of applying it, but not the rationale and logic behind this powerful method. Here I will present an analogy which I often find useful when thinking about induction. We are going to use every math teacher's favorite example, using the method of induction to prove that the sum of first n positive integers equal n times n plus 1 divided by 2. Let me run through the method we are all taught briefly. To prove the statement, we would first need to show that the statement is true for n equals 1, or as some people prefer, P1 is true. This is called proving the base case, and usually it's the easier part of the induction proof. After this, we will usually assume the case statement to be true. You might know this as the induction assumption step. After this, using the statement we have assumed to be true, we have to prove that the k plus 1 statement to be true. This is usually the hardest part of the question. In the example we use, we can simply add k plus 1 to both sides of the equation. Doing this, the left-hand side will be the sum of first k plus 1 positive integers, while the right-hand side could be factored to give the expression we desired. We then declare the problem to be solved using the principle of mathematical induction and move on to the next question in the exam or the worksheet. Now, this is a perfectly normal routine for solving induction problems. But let's address the elephant in the room. Have you ever wondered why we do the things we did? Why do we have to assume that the case statement is true? And how does proving the k plus 1 statement help with proving the statement for all positive numbers? I've always found the domino model useful in explaining the method of induction. Think about what we have set out to do. Basically, we want to prove that the formula for the sum of first n terms is true for all positive integers n. We can break this up into infinitely many statements. P1 would be the case where n equals 1, P2 is a case where n equals 2, and so on. We can manually check that P1, P2 are true, but there's no way for us to do this to all positive integers, as there are infinitely many of them. Imagine that we now set up all the statements P1, P2, P3, and so on as dominoes, one following the other, in a straight line. Assume that the nth domino will be toppled if we manage to prove Pn, or the validity of the nth statement. If we verify that P1, P2, and P3 are true independently, this would be equivalent to toppling the first, second, and third dominoes manually. To prove that the statement is true for all positive integers n is the same as toppling all the dominoes. If you think there's a faster method to do this other than toppling each of the dominoes separately, then you are right. Let's see how the principle of mathematical induction comes to our rescue. Now, proving the base case, P1, would be akin to toppling the first domino. And as mentioned earlier, we do not have all the time in the world to manually topple the second, third, fourth domino, and so on, by checking each of the statements independently. If you remember, the next step in our induction process would be to assume that the case statement is true, or using our domino model to assume that the case domino is toppled. What happens next is, we use the fact that pk is true to prove that pk plus 1 is true. In our domino language, you can understand it as proving the toppling of the k domino implies the automatic toppling of the k plus 1 domino. Now, although it might be apparent in real life that toppling a domino will lead to the next one in line to topple as well, but we are merely using this as an analogy here to explain the method of induction. We would have to prove that the domino chain effect would indeed take place after we toppled a certain domino. In the induction process, remember that we use the case statement together with some additional correct mathematical statement or manipulation to prove the k plus 1 statement. In our domino language, to prove that the next domino in line will topple, we will invoke the fact that the earlier domino has been toppled and couple this with factual information about how the dominoes are tilted and the laws of physics. This is usually the hardest part of the entire induction proof. In most cases, the base case is easy because we are only dealing with a single case. Intuitively, you can imagine toppling over the first domino is easy, but proving that the chain effect would continue indefinitely is hard. However, if we do manage to obtain a proof, then we essentially created a chain domino effect. Our base case would show that P1 is true, and the domino effect we proved above allows us to conclude that P2 is true as well. Continuing in this manner, since P2 is true, we see that P3 is true by the domino effect, and the chain propagates to all natural numbers, allowing us to show that our initial statement holds for all natural numbers. A final question for you to ponder. The induction allows us to show that a statement is true for all positive numbers n, but can we adapt it to the system of all integers, rational numbers, and even real numbers? The extension to all integers and even rational numbers is possible, and it works quite similarly to the case above. But the extension to induction of real numbers involves concepts which we will not cover now. Do stay tuned for future videos if you are interested about the above. Alright, we have come to the end of this video, and I hope to see you in the next one.